Okay, thank you.
Tom's online, ready to go.
Thanks. And we'll move on to Tom already. I hope you're there, Tom.
Hello, yes, can you hear me?
Yeah, we can hear you loud and clear. So
Wonderful.
far away.
Hi. First of all, thank you for inviting me to this conference, and thank you to all the speakers so far for some really interesting presentations. My name's Tom. I'm a PhD student from the Free University in Amsterdam, along with Roland. And like Roland, I'm also working with drones, although looking at the slightly different aspect of the emissions story at the patchiness of fire scars, and also if we can establish how to measure fuel loads from aerial imagery from drones. This is kind of going to be a two-part presentation. The first part's mostly about internal fire scar mapping and how to map patchiness in detail from drones. And the second half is more about the fuel load aspect of things. But just before I go into either of those, I'm going to give you a little quick overview of the kind of drones that I'm using and how we get data from that. The workhorse of my project is this particular drone. It's a Phantom P4, and it was designed for agricultural use, for crop surveys, but we've repurposed it to survey plots that Jeremy Cameron and colleagues have been laying in Australia and in Africa. It has several bands, of which two are in the near infrared side of the spectrum, which, as I'm sure some of you are aware, this is very useful for vegetation mapping for things like NDVI, for example, which gives us a lot of information about plant health and biomass. A survey, we have special software for the surveying, and per survey we can get about 2 to 4 hectares with a ground resolution of about 5 centimeters, which is pretty good. You can see a lot of detail, especially in the surface layers of fuel, the grass and the litter layers, which is very useful for mapping surface fuel biomass, which is, especially in the early dry season, most of what burns in the savannas. And on one of these flights, the drone will take a few hundred pictures. And at the end of the flight, to create this orthophoto, we'll stitch them all together, and the end result looks a little something like this. And this is an example from, I think, Kafue National Park in the late dry season when we were there in 2021. Yeah, so this is what it looks like when all the images are stitched together. Hopefully, I don't know how much detail you've got on the screen there, but hopefully you can see that you can pick out quite a bit of detail just from the canopy, but also little patches of bare soil, for example, and areas where the grass is perhaps a little more brown, or where there's a really sort of absence of grass entirely. We do this for both pre and post fire flights. So when a fire goes through the area, we can fly this again. And that's when we start looking at things like internal fire scar patchiness. And I want to just take a little bit of time now to go through exactly what I mean by that, because there's different types of unburned area, and some of which is relevant for internal fire scar patchiness and some of it is not. For which end I'm going to use this example, which is from a different site, this time I think in Australia. And there are, first of all, there's a very, hopefully you can all see, there's a very obvious, most of the image is covered with burned area. But there are a few patches where the vegetation hasn't been burned. Some of that is important to us and some of that is not. So this part, for instance, is unburned, but we know from being on site that this is outside of the fire scar. This is, in fact, where the fire was started from. So when we're looking at patchiness inside fire scars, we don't want to consider this part. We also don't want to consider the canopy, because although the canopy is unburned, the area underneath the canopy is burned. So that has to be considered as an area which the fire has passed through and not patchiness. which I'll go through in a moment how we filter those out. What we're really interested in only is these kind of areas, the areas which are where the surface level has been untouched by fire. The outside of the fire scar is relatively straightforward to clip out. We simply use the internal part of the scar by, for example, just clipping out with a shapefile. But the tree canopy is a little bit more complicated. And to get that out, I'm sorry, skip that one. To get that out, we isolate each canopy object inside a bounding box, and we have a look at the perimeter around it. And essentially, if the burned area in the perimeter is less than 30%, so if all those individual highlighted pixels, less than 30% of those are burned, then the canopy object is reclassified as unburned. And if that's not the case, then it's burned. And the reason why we have such a skew towards burned area is that from experience, generally, if a tree or shrub canopy has been touched, as it is sort of the pixels touch each other from burned and canopy, then most of the time underneath the canopy, it is burned as well. So we have a slight leaning towards classifying things as burned rather than unburned, but from experience, that seems to be reasonable. And if we filter out all those objects and we filter out smaller objects, I think we have a threshold size of about 5 square meters, just because more often than not, those are artifacts of the classification or noise that we're not interested in. We end up with something like this. We have largely burned area with a few patches of unburned vegetation. And over the last couple of years of working on these kind of projects, we've surveyed several different rainfall gradients, as Cameron alluded to earlier. And we put many, many different plots and done many different drone flights in all these different rainfall gradients. And we've done a patchiness analysis for all of those different rainfall gradients. And in the figure here, just to go through it, the shape of each violin object indicates the sort of spread of the data. So where it's fatter, you have more weight, and where it's thinner, there's only a few data points in that region. On the x-axis are rainfall gradient groupings, so by 500 millimeters per year. And each rainfall bin is split into early dry season plots on the left and late dry season plots on the right. For lower rainfall, for drier regions, there isn't really a great distinction between early and late in terms of internal fire scar patchiness. And this kind of holds true up to about 1,000 millimeters per year. Once you get past that, you do really start to see a much more significant difference between patchiness in early fires and late fires. And I think it's also worth noting that the late fires in the higher rainfall region are far more completely burned than, for example, late fires in the lower rainfall. And currently the working theory around that is that it's to do with fuel connectivity. So if you have a lower rainfall region where the fuel is slightly sparser, then perhaps you have more opportunities for fire to stop around certain patches. Whereas when you have a more complete and continuous fuel layer, especially in dry conditions in a higher rainfall region, that allows for a much more complete burn. This, however, doesn't mean that fires aren't smaller in the early dry season everywhere, because that is the case, and that's what we found. And if you compare internal fire scar patchiness to plot scale burned area, you really see that in the early dry season, there is a significantly lower burned area from drone imagery as well as other satellite analyses than you do for late dry season when you have a much higher burned area. We're going to skip on to the next section now and just briefly go into how we can determine, how we're looking into determining fuel load from drone measurements. And really the overarching aim here is to scale up all of those ground measurements that others have been talking about earlier in this session to drone and then satellite data, so that we can really get a regional picture of biomass from the ground up, from bottom up measurements. And there's a few steps to this. I'll go through them one by one in a minute. But firstly, we have in the drone image the transects that have been laid, and we can connect those to the imagery using ground control points. We take all the data from those transects along with a meteorological history of the plot, use a machine learning model to train a machine learning model on this data to then apply that model to a larger satellite project, for example, Sentinel or Landsat. So a picture that you're perhaps familiar with already from earlier presentations, but we first put in some transects. We measure fuel load in different classes: grass, litter, woody debris, tree count, as well as shrub count. And we can connect that to a specific location in a drone image. As the picture on the right shows, highlighted in red, is just one of the 3 transects in this image. And that gives us a library of a few hundred transect images, as it were, from drone data. And in each one of these images, from these images, we can collect a whole host of different data from the drone. So that includes, but is not limited to, a class percentage. So how much proportionally of grass cover there is, how much proportionally of canopy cover, how much bare soil there is, but also various vegetation indices like NDVI, and from the stereophotography, from photogrammetry, we can also get a canopy height map of the area. And all of this data we'll take from each transect and we'll pop it into an enormous database with a whole host of different variables, and train a machine learning model to predict biomass on the basis of this. This works very well for surface fuels, so grass and litter, and we can get a really good picture of how much grass there is per, roughly in this instance, 20-meter pixel, and for litter as well. We're currently working on a better relationship between specifically the canopy height model and the allometric equations we have for regional trees, to get a better sense of the biomass for standing woody vegetation, for shrubs and trees. And we're hopefully in the very near future going to be able to use these images and these connections between ground measurements and drone data, expand biomass measurements, ground measurements, to a larger regional scale using satellites. That's it from me, I think. If there are any questions, I'm happy to answer them now.
That's a good one. Tom, in a previous work, you've actually demonstrated from your drone assessments of fuel loads that you get a very good relationship, a very high relationship, particularly with, I suppose we'll call it fine fuel biomass. I mean, you didn't present any data here as such. What is the future of drone estimates of biomass for, let's say, fine fuels and the like at landscape scales?
Yeah, as you rightly pointed out, the fine fuel is more or less already there. I think we can get a good sense of grass and litter cover, especially for most of the areas where we've laid plots. So in Southern Africa and Northern Australia. And I'm fairly confident in those measurements, certainly.
How confident?
I would hesitate to put a number on it, although I think I would say that probably we're working with us between 20 to 30% error margin for biomass measurements on a 20-meter scale.
Yeah, it's good. No worries. Look, thanks very much for your time, and go back to enjoying your day in that part of the world.